Somewhere above the surface of our planet, invisible to the naked eye, a wall of charged particles and twisted magnetic field lines is currently racing through the vacuum of space at hundreds of kilometers per second, heading directly for Earth. It didn't come from nowhere. On August 14th, an arching filament of solar material lifted off the surface of the sun and hurled a massive cloud of plasma into interplanetary space. Scientists have been tracking it ever since, watching its models shift and sharpen with every new hour of data, and now, as it closes the final stretch of its journey, forecasters expect it to slam into Earth's magnetic field within hours. But this isn't just another routine space weather update. This storm arrives on the heels of something far stranger, a wave of new scientific research suggesting that solar activity and the trembling of Earth's own crust may be connected in ways nobody fully expected. Today, we're diving into both halves of this story. The solar storm currently. Let's start with what's actually happening above our heads right now. The sun is not the calm, steady yellow disk it appears to be from Earth. It's a churning, roiling ball of plasma wrapped in magnetic fields so complicated that even the world's most advanced models struggle to fully predict its behavior. Every 11 years or so, the sun cycles through a rhythm of activity, swinging from quiet periods known as solar minimum to chaotic, eruption-heavy periods known as solar maximum. Right now, in 2026, we are living through one of the most active windows of that cycle in years. Over recent months, the sun has fired off dozens of significant flares in rapid succession, including several X-class eruptions, the most powerful category flares can reach. Some of these eruptions have ranked among the strongest recorded in years, with intensities exceeding X8 and even brushing X9, numbers that make solar physicists sit up and pay very close attention. To understand why an event like the one currently barreling toward Earth matters, it helps to understand the difference between two things that often get lumped together in casual conversation: solar flares and coronal mass ejections. A solar flare is a sudden, intense burst of radiation released when tangled magnetic field lines on the sun's surface snap and reconnect in a process scientists call magnetic reconnection. That reconnection releases an almost unimaginable amount of energy in a matter of minutes, equivalent to millions of hydrogen bombs detonating simultaneously. Because a flare is pure radiation, it travels at the speed of light. Meaning if the sun unleashes a flare aimed at Earth, the effects arrive here in roughly 8 minutes, with essentially no warning. A coronal mass ejection, or CME, is a different beast entirely. Rather than a burst of radiation, a CME is an enormous cloud of magnetized plasma, physically hurled outward from the sun's corona into space. Unlike a flare, a CME doesn't travel at the speed of light. It takes anywhere from 1 to 3 days to cross the 93 million miles separating the sun from Earth, giving scientists a crucial window to track it, model its trajectory, and issue warnings before it arrives. Flares and CMEs often occur together, born from the same violent magnetic upheaval, but not always. Sometimes, a powerful flare fires off with no ejection at all. Other times, a CME launches from a region that produced only a modest flare. It's the CME, this slower-moving cloud of solar material, that is currently the center of attention, because it's a CME that left the sun on August 14th and is now closing in on Earth. Current models suggest the leading edge of this magnetic flux rope, essentially a twisted tube of plasma and magnetic field lines stretched across millions of miles of space, will strike Earth's magnetosphere later today, setting off what scientists call a geomagnetic storm. When a CME's magnetic field connects with Earth's own protective magnetic bubble, it can trigger a cascade of electromagnetic disturbances, compressing our planet's magnetosphere, injecting energetic particles into the upper atmosphere and lighting up the sky with the shimmering colors we know as the aurora. Forecasters are currently expecting a G1 or minor geomagnetic storm as the most likely outcome, though there remains a real chance conditions could escalate to a G2 or moderate storm if the incoming magnetic field orients itself southward when it makes contact with Earth's field, a configuration that tends to amplify geomagnetic effects. For most people, a storm of this magnitude means one thing above all else: a good chance of aurora, potentially visible farther from the poles than usual, painting the night sky in ribbons of green, pink, and violet for sky watchers lucky enough to have clear conditions overhead. But the story doesn't end with pretty lights in the sky, and it's here that things take a genuinely strange turn. In the days following this CME's arrival, scientists expect the geomagnetic environment to remain unsettled, partly because of the storm itself, and partly because of a second, entirely separate space weather feature lining up right behind it. A coronal hole, a region on the sun where the magnetic field opens outward into space rather than looping back on itself, has been pouring out a stream of fast solar wind with speeds reaching as high as 700 kilometers per second during its last pass. As that coronal hole rotates back into position facing Earth in the days ahead, forecasters anticipate another round of unsettled to possibly stormy conditions, layering fast solar wind on top of the CME's lingering effects. In other words, this isn't a single, isolated event. It's the opening act of what could be a stretch of turbulent space weather extending across several days. Now here's where the story gets genuinely unusual, and where the phrase strange seismic burst earns its place in this conversation. For decades, the relationship between solar activity and events happening deep within Earth's crust was considered, at best, a fringe idea, the kind of connection dismissed by mainstream geophysics as coincidence dressed up as correlation. But a growing body of new research is forcing scientists to take a second, more careful look. Earlier this year, researchers proposed a striking new framework suggesting that disturbances in Earth's ionosphere, the electrically charged layer of our upper atmosphere that reacts directly to solar activity, might be capable of sending feedback forces down into the crust below. The mechanism they describe involves electrostatic coupling between the ionosphere and the ground, essentially an electrical relationship between the charged particles high above us and the rock and soil far beneath our feet. According to this model, it isn't necessarily a one-way street where the sun disturbs the sky and nothing else happens. Instead, researchers propose a two-way interaction, where processes occurring inside the Earth can influence conditions in the ionosphere, and disturbances originating in the ionosphere might, under the right conditions, send electric forces back downward into the crust. To be clear, and this matters enormously for understanding the science responsibly, nobody involved in this research is claiming that solar storms directly cause earthquakes. The scientists behind this framework have been careful to frame their proposal as a possible feedback mechanism, not a proven trigger. And they explicitly note that timing alone does not prove cause and effect. But the timing they've observed is striking enough to warrant serious investigation. Researchers pointed to several major earthquakes, including Japan's devastating Noto Peninsula earthquake, as events that occurred within a window of unusually intense solar flare activity. They have also referenced earlier examples, including seismic waves recorded shortly before a massive volcanic eruption, raising fresh questions about whether some geological events might be preceded by detectable signals that current monitoring systems simply aren't designed to catch. If this connection holds up under further scrutiny, and that remains a genuine if, the implications could be significant. Earthquake prediction has remained one of the most stubbornly unsolved problems in modern science, a field where decades of research have produced excellent hazard mapping, but almost no reliable short-term forecasting ability. If ionospheric disturbances linked to solar activity really do interact with crustal stress in measurable ways, it could open an entirely new avenue for monitoring, one that watches not just the ground itself, but the electrically charged sky above it, for early warning signs currently invisible to existing seismic networks. It's important to sit with the uncertainty here rather than rush past it. Science doesn't move from a single study to settled fact, and a hypothesis, this new, this early, and this counterintuitive, deserves exactly the kind of scrutiny it's currently receiving from the broader geophysics community. Skeptics have rightly pointed out that Earth experiences intense solar activity far more often than it experiences major earthquakes, meaning any individual case of solar storm followed by earthquake could easily be coincidence, especially given how frequent significant flares have become during this particularly active stretch of the solar cycle. Correlation, as any good scientist will tell you, is not causation. And finding a handful of matching timelines is a very different thing from establishing a proven physical mechanism. Still, the mere possibility is enough to make today's incoming solar storm feel like more than just another aurora forecast. As this CME connects with Earth's magnetosphere and stirs up geomagnetic activity over the coming days, some researchers will likely be watching not just satellite data and power grid monitors, but seismic networks as well, curious whether this particular storm produces any unusual patterns worth adding to the growing data set behind this emerging hypothesis. Beyond the seismic questions, there are more immediate, well-established reasons to pay attention when a CME like this one makes contact with our planet. Geomagnetic storms, even relatively minor ones, ripple outward into systems we rely on every single day, often in ways most people never notice unless something actually breaks. Satellites orbiting Earth can experience increased atmospheric drag during geomagnetic storms as the upper atmosphere heats and expands, subtly altering orbits and forcing operators to make small corrections to avoid problems. GPS accuracy can degrade during stronger storms, as disturbances in the ionosphere distort the signal satellites send down to receivers on the ground, an effect that matters enormously for industries like aviation, shipping, and precision agriculture that depend on centimeter-level accuracy. Radio communication, particularly high-frequency radio used by aviation, maritime, and emergency services, can also suffer as the same ionospheric disturbances that scatter GPS signals can absorb or scramble. Radio waves passing through the upper atmosphere, sometimes causing temporary blackouts on the sunlit side of Earth during the peak of a flare's radiation burst. And in more extreme cases, geomagnetic storms have been known to induce electrical currents in long conductors here on the surface, including power lines and pipelines, occasionally straining transformers and, in rare historical cases, contributing to regional power outages. It's worth emphasizing that today's storm, currently forecast at G1 to possibly G2 intensity, sits nowhere near the extreme end of that spectrum. For comparison, the most powerful geomagnetic storm in recent memory struck Earth in May 2024, when a series of enormous coronal mass ejections combined to create a G5, or extreme geomagnetic storm, the strongest event of its kind since 2003. That storm produced auroras visible as far south as Florida and Mexico, an extraordinary sight for millions of people who had never witnessed the northern lights in their lives. It also briefly disrupted GPS-guided agricultural equipment during a critical planting season and forced satellite operators worldwide into a state of heightened alert. Today's storm is a far gentler cousin of that event, but it serves as a useful reminder of just how directly connected our modern technology-dependent lives remain to the unpredictable moods of a star 93 million miles away. Scientists and government agencies have increasingly begun warning that society may be underestimating the broader risk posed by truly extreme space weather events. Reports commissioned by risk analysts in recent years have modeled worst-case scenarios in which a storm on the scale of the historic 1859 Carrington event, widely regarded as the most powerful geomagnetic storm in recorded history, strikes a modern, satellite-dependent world. The conclusions from the SMI kind of modeling are sobering. Potential disruptions to satellite constellations, GPS networks, and power grids on a scale that could take months, not days, to fully repair in the worst affected regions. It's a scenario nobody expects to unfold from today's relatively modest CME, but it's part of why space weather agencies around the world take even minor storms seriously, treating each one as both a manageable event in its own right and a valuable data point for understanding how prepared our infrastructure really is. So what should we actually expect over the coming days? Forecasters anticipate the CME's leading edge will connect with Earth's magnetosphere and spark the beginnings of geomagnetic disturbance, most likely settling into G1 conditions, with a real possibility of brief G2 level activity if the storm's magnetic orientation cooperates. Skywatchers at higher latitudes should keep an eye on the sky after dark, as this kind of storm often produces visible aurora even for casual observers who've never specifically chased the northern lights before. In the days that follow, as the CME's influence begins to fade, that fast-moving stream of solar wind from the nearby coronal hole is expected to arrive, potentially extending the unsettled conditions a little further, though with somewhat more uncertainty in the forecast, given how much that particular solar feature has evolved since its last pass. Meanwhile, the quieter, stranger story running underneath all of this, the question of whether Earth's crust and the sun's outbursts are speaking to each other in ways we're only beginning to detect, will continue playing out far more slowly in research papers, seismic archives, and careful statistical comparisons stretching across years rather than days. It's the kind of question that doesn't resolve itself in a single dramatic headline, but instead gets chipped away at gradually, one data point, one earthquake, one solar cycle at a time, until either a genuine pattern emerges or the correlation quietly fades back into coincidence. What makes moments like this genuinely fascinating isn't certainty. It's the fact that we're watching two enormous, largely unpredictable systems, one hovering in space and one buried deep beneath our feet, and beginning to ask, seriously, for the first time, whether they might be connected in ways textbooks never taught us. Whether or not this particular storm ends up meaning anything for the seismic side of that question. It's already meaning something for the sky above us tonight, and for the scientists watching every second of its arrival with the kind of quiet excitement that only comes from studying a star that still has plenty of secrets left to reveal. For now, all eyes remain on the incoming plasma cloud, the satellites tracking its approach, and the ground-based instruments, quietly logging everything that happens the moment it arrives. Whatever this storm turns out to be, gentle or unruly, ordinary or strangely coincidental, it's a reminder that Earth doesn't exist in isolation. We are, and always have been, living inside the outer reach of the sun's atmosphere, tethered to its moods by an invisible magnetic thread 93 million miles long, and every so often that thread gives a tug strong enough for all of us to notice. If this story fascinated you, don't forget to like and subscribe for more real-time coverage of the space weather events unfolding above our heads, and the emerging science trying to explain how deeply connected our restless star and our restless planet might really be.